Our story begins long, long ago, billions of years before now. Think about the vastness of space. It is filled with stars, trillions of them. Each star is a sun, like our own. These stars are not eternal. They are born, they live, and then they die. Our own sun is one of these stars. It is special to us, of course. It gives us light and warmth. It is the heart of our solar system. But its birth story is a cosmic tale repeated across the universe. It is a story of dust, gas, and the powerful force of gravity. Imagine a giant cloud floating in space, not a cloud like you see in Earth's sky. This cloud was enormous, vast beyond imagining. It was cold and dark. This cloud was made mostly of hydrogen and helium gas. These are the simplest and most common elements in the universe. There were also tiny bits of dust. These dust grains were made of heavier elements, elements forged in the hearts of ancient stars that had lived and died. This giant molecular cloud was our solar system's nursery. It held all the raw materials for our sun and all its planets, including our Earth. What made this huge cloud start to change? Something disturbed it. Perhaps it was the shock wave from a nearby exploding star. A supernova, this cosmic push, caused parts of the cloud to become denser. Gravity then took over. Gravity is the force that pulls everything together. The denser regions began to pull in more gas and dust. Slowly, over millions of years, these regions started to collapse. As they collapsed, they began to spin. Like a skater pulling in their arms, the spinning got faster and faster. The cloud started to flatten into a disk. At the very center of this spinning, collapsing cloud, something amazing happened. The material became incredibly dense and hot. The pressure was immense. Hydrogen atoms began to fuse together. They formed helium atoms. This process is called nuclear fusion. It releases a tremendous amount of energy. This energy pushed outwards, balancing the inward pull of gravity. A star was born. This young star was our sun, our proto-sun. It blazed with light and heat. It was the anchor of a new solar system just beginning to form around it. The cosmic stage was set for planets to emerge. Around our young blazing sun, a vast disk continued to spin. This was not a solid disk. It was made of the leftover gas and dust from the sun's formation. Scientists call this a protoplanetary disk. Think of it as a giant cosmic frisbee. It stretched out for billions of kilometers. All the future planets, moons, asteroids, and comets of our solar system would form from this swirling material. It was a dynamic place, full of motion, full of potential. The sun sat at its hot center, while the rest of the disk slowly cooled as you moved further away. What was this protoplanetary disk made of? It was mostly gas, hydrogen and helium, just like the sun. But it also contained those important tiny dust grains. These grains were like specks of cosmic soot. They included silicates, which are rocky materials, and carbon compounds. Further out in the disk, where it was colder, there were also icy particles, water ice, methane ice, ammonia ice. These different materials were spread throughout the disk. Their distribution was not random. It depended heavily on the temperature at different distances from the young hot sun. The temperature within this disk was not uniform. Close to the fiery young sun, it was incredibly hot, too hot for icy materials to remain solid. They vaporized. So, the inner part of the disk was mostly rocky dust grains and metals. Further away from the sun, the temperatures dropped significantly. Beyond a certain point, called the frost line or snow line, it was cold enough for water ice to form and survive. Even further out, exotic ices like methane and ammonia could condense. This temperature gradient played a crucial role in determining what kind of planets would form where. This giant swirling disk of gas and dust was the birthplace of worlds. It was a cosmic construction site. Everything needed to build planets was there. All it took was time and the right physical processes. The sun shone at its heart. The disk spun around it. The materials were sorted by temperature. The scene was set for the next amazing chapter in our solar system's story. The slow, patient process of planet formation was about to begin. From tiny specks of dust to giant worlds, the universe was at work building our future home. Inside the protoplanetary disk, those tiny dust grains began to interact. At first they were just drifting, but they were not alone. There were countless others. Sometimes they would gently bump into each other. Little by little they started to stick together. Maybe static electricity played a role, like dust bunnies under your bed, or perhaps sticky organic coatings helped them clump. These first clumps were very small, microscopic, but it was a start. The first step in a long journey from dust to planets, a process of gradual accumulation. These tiny clumps continued to grow. As they got bigger, their gravity, though still very weak, started to help. They attracted more dust, and they attracted other small clumps. The clumps grew into pebble-sized objects. Then these pebbles gathered together. They formed larger bodies like rocks, then bigger rocks. Imagine a slow-motion cosmic hailstorm, but instead of ice, it was dust and rock. And instead of falling, everything was orbiting the sun. These growing objects swept through their paths, gathering up more material. The disk was slowly clearing as material was incorporated into these larger bodies. Eventually, these objects grew to be a few kilometers across. Some were even larger. Scientists call these mini-planets planetesimals. There were many, many of them, thousands, perhaps millions. Each one was a building block for a future planet. They all orbited the sun within the protoplanetary disk. Their orbits were not always perfectly stable. They pulled on each other with their growing gravity. Sometimes their paths crossed. This led to the next crucial stage in planet formation: collisions. The solar system was a cosmic demolition derby. Collisions between planetesimals were common. Some collisions were gentle. If two planetesimals bumped into each other slowly, they might merge. They would stick together, forming an even larger body. This is called accretion. It's how planets grow, but not all collisions were gentle. Some were violent. If planetesimals crashed into each other at high speeds, they could shatter. They would break apart into smaller pieces, but even these pieces could later recombine. Over millions of years, through countless collisions and mergers, the largest planetesimals swept up most of the material in their paths. They became the dominant bodies in their orbits. Through this chaotic process of accretion and collision, larger bodies began to emerge. These were the protoplanets, the embryos of future planets. Our own Earth started this way. As a growing protoplanet in the inner part of the solar system, it gathered more and more planetesimals. Its gravity became stronger. It pulled in material from a wider and wider zone around its orbit. The young Earth grew rapidly. It was on its way to becoming the planet we know, but it looked very different back then. It was a hostile and alien world. The early Earth was incredibly hot. All those collisions generated enormous heat, each impact by a planetesimal released energy. This energy melted the rock. The decay of radioactive elements within the planet also added to the heat. So the young Earth was a molten ball, a glowing sphere of liquid rock. Its surface was a sea of lava. There was no solid ground, no oceans, no atmosphere as we know it, just an inferno. Volcanic activity was constant and widespread. It was a truly hellish landscape, a planet still in the throes of its violent birth. As Earth remained molten, something important happened. The materials within it started to separate. Heavy elements like iron and nickel were denser. They sank towards the center of the planet. Imagine a giant cosmic centrifuge. The lighter, less dense, rocky materials called silicates floated upwards. They formed the outer layers. This process is called planetary differentiation. It's a key step in the formation of rocky planets. It gives them their layered internal structure. Without differentiation, Earth would be a very different and likely uninhabitable place. This differentiation created Earth's distinct layers. At the very center, a dense core of iron and nickel formed. This core is partly solid and partly liquid. It generates Earth's magnetic field, which is vital for protecting life. Above the core is the mantle, a thick layer of hot, slowly flowing rock. And on the very outside, a thin, cooler crust of solid rock began to form as the surface slowly radiated heat into space. The young Earth was taking shape. It was becoming a structured planet. But it was still a very dangerous and dynamic place, far from the blue marble we see today. Section 5. The Moon's Violent Kiss, a Cosmic Collision. Our young Earth was not alone in its journey around the Sun. The early solar system was a crowded place. There were still many large planetesimals and protoplanets whizzing around. Some of these were on unstable orbits. Collisions were still happening. One of these rogue bodies was particularly large. Scientists estimate it was about the size of Mars. They have given it a name: Theia. Theia's orbit eventually brought it onto a catastrophic collision course with the young Earth. This was not just another small impact. This was a planet-sized smash-up. The impact of Theia with Earth was an unimaginable event, a cosmic catastrophe on a grand scale. Theia struck Earth at a glancing angle, but with incredible force. The energy released was immense, far greater than any volcanic eruption or asteroid impact Earth has experienced since. Both Theia and a large part of Earth's mantle were vaporized and ejected into space. A colossal cloud of molten rock and superheated gas briefly surrounded our planet. This was the most significant single event in Earth's early history. It profoundly shaped both our planet and its future. The debris from this giant impact didn't just fly off into space. A huge amount of it was captured by Earth's gravity. It formed a ring of hot, molten material orbiting our planet. This ring would have looked spectacular. A glowing band of rubble circling the wounded Earth. Over time, the material in this ring began to clump together. Gravity pulled the pieces towards each other. Smaller clumps merged to form larger ones. It was like a miniature version of planet formation happening right in Earth's backyard. This process was relatively quick, perhaps taking only a few thousand years or even less. Eventually, most of the material in the ring coalesced to form a single large body. This body was our moon, the moon we see in our sky every night. This giant impact hypothesis is the leading theory for the moon's formation. It explains many things: why the moon is relatively large compared to Earth, why its composition is similar to Earth's mantle but poor in iron. The moon became Earth's constant companion. Its gravity stabilizes Earth's tilt. It causes tides in our oceans. The violent birth of the moon was a crucial step in making Earth the planet it is today. Section 6. Location, Earth's Goldilocks zone. The Earth's position in the solar system is incredibly important. It orbits the Sun at just the right distance, not too close, not too far away. This special region around a star is often called the habitable zone. Some people call it the Goldilocks zone. You remember the story of Goldilocks and the three bears? One bowl of porridge was too hot, one was too cold, but one was just right. For a planet to potentially support life as we know it, its temperature needs to be just right for liquid water to exist on its surface. If Earth were much closer to the Sun, it would be a very different world. It would be like Venus. Venus is closer to the Sun than Earth is. Its surface temperature is scorching hot, hot enough to melt lead. Any oceans Venus might have had in its distant past boiled away long ago. The thick atmosphere of carbon dioxide traps heat, creating a runaway greenhouse effect. Life as we know it could not survive there. So, being too close to the star is bad news for water and therefore for life as we understand it. Proximity to the Sun dictates a planet's surface temperature. Now imagine if Earth were much farther from the Sun. It would be like Mars or even more distant planets. Mars is further from the Sun than Earth. It is a cold desert planet. While there is evidence that Mars once had liquid water, today any water on its surface is frozen. Temperatures on Mars are usually well below freezing. If Earth were in Mars's orbit, or even further out, our oceans would freeze solid. The planet would be an icy wasteland. Again, not a good place for life as we know it to thrive. Distance is key for planetary habitability, so Earth is in this special Goldilocks zone. Our orbit keeps us at a distance where water can be a liquid. Not too hot to boil it all away, not too cold to freeze it all solid. Liquid water is essential for all life forms on Earth. It is a universal solvent. It transports nutrients. It facilitates chemical reactions. Earth's perfect positioning is a crucial factor that allowed life to arise and flourish here. It is a remarkable stroke of cosmic luck, or perhaps an inevitable outcome in a vast universe filled with planetary systems. Our location is truly special. Section 7. Waterworlds, the arrival of oceans. When Earth first formed and cooled enough to have a solid crust, it was still a very dry place. The intense heat of its formation and the early solar wind would have driven off most volatile compounds, including water. So a big question arises: where did all the water that fills our vast oceans come from? How did Earth transform from a dry, rocky ball into the blue marble teeming with water that we see today? The answer likely involves a combination of cosmic deliveries and contributions from the planet itself. This transformation was vital for life's emergence. One prominent theory suggests that Earth's water was delivered by icy bodies from the outer solar system. Comets and asteroids. Comets are like dirty snowballs. They are mixtures of ice, dust, and rock. Asteroids, especially those from the outer asteroid belt, can also contain significant amounts of water ice. During the early chaotic period of the solar system, known as the Late Heavy Bombardment, Earth was pummeled by these objects. Each impact by an icy comet or water-rich asteroid would have delivered water to the young planet. Over millions of years, these contributions accumulated. Another source of water could have been from within Earth itself. When the planet formed, water molecules might have been trapped within the minerals of the rocks that accreted to build it. This is called hydrated minerals. As Earth's interior heated up due to radioactive decay and residual heat from formation, these rocks melted. Volcanic activity was rampant on the young Earth. Volcanoes released massive amounts of gases from the planet's interior. This process is called outgassing. Among these gases was water vapor, or steam. A significant portion of Earth's water may have come from its own mantle. As the Earth's surface continued to cool, this water vapor in the primitive atmosphere began to condense. It formed clouds. Then it began to rain. Not just a shower, but a deluge that lasted for centuries, perhaps even millennia. This relentless rain slowly filled the low-lying basins and craters on Earth's surface. Vast oceans began to form. These early oceans were likely very different from today's. They might have been hotter, more acidic, and full of dissolved minerals from the young crust. But they were oceans nonetheless. Liquid water now covered a large part of Earth's surface, creating the conditions necessary for life to begin its incredible journey. Section 8. The spark of life, from molecules to microbes. With oceans of liquid water, a reasonably stable crust, and a protective atmosphere beginning to form, the stage was set on Earth for something truly extraordinary: the emergence of life. This is one of the biggest mysteries in science. How did non-living chemicals organize themselves into living organisms? We don't have all the answers yet, but scientists are piecing together clues. It likely happened in the oceans, perhaps in shallow pools warmed by the sun, or maybe near deep-sea hydrothermal vents. These vents spew out chemicals from Earth's interior, providing energy and raw materials. The early Earth's environment was rich in simple molecules: carbon dioxide, water, nitrogen, methane, ammonia. Energy was also abundant, from sunlight, especially ultraviolet radiation, from lightning strikes in the atmosphere, from the heat of volcanic activity and hydrothermal vents. In this primordial soup, these simple molecules began to react with each other. They formed more complex organic molecules. These are the building blocks of life, molecules like amino acids, which are the components of proteins, and nucleotides, which make up DNA and RNA, the carriers of genetic information. Over vast timescales, these complex molecules became more organized. Perhaps they were concentrated on the surfaces of clay minerals, or enclosed within tiny bubbles of fat-like substances, forming primitive cell membranes. Eventually, a truly remarkable molecule arose, one that could make copies of itself, a self-replicating molecule. This was a crucial step. It allowed for inheritance and evolution, the first entities that could reproduce and pass on their characteristics to offspring. These were not yet true cells, but they were on the path to becoming life. The earliest forms of life on Earth were incredibly simple. They were tiny microbes, single-celled organisms, similar to bacteria we see today. They probably appeared around 3.5 to 4 billion years ago. For billions of years, these simple microbes were the only life on our planet, but they were revolutionary. Some of them evolved a new trick: photosynthesis. They learned to use sunlight to make their own food. A byproduct of this process was oxygen. Slowly, these tiny organisms began to pump oxygen into the atmosphere, profoundly changing Earth's environment and paving the way for more complex life to evolve. Section 9. An ever-changing home, Earth's ongoing story. Our planet Earth is not a static museum piece. It did not simply form and then stay the same. It is a dynamic, ever-changing world. Its story continues to unfold. Even now, the continents we live on are not fixed in place. They drift across the surface of the planet. This is called plate tectonics. Continents collide, pushing up massive mountain ranges like the Himalayas. They also pull apart, creating new ocean basins. Earthquakes and volcanoes are constant reminders of the powerful forces at work beneath our feet. The face of our planet is always being reshaped. Life, too, has been on an incredible journey of evolution. From those first simple microbes, life diversified. It became more complex. Multicellular organisms appeared. Plants colonized the land. Fish evolved in the oceans. Amphibians crawled onto the shores. Reptiles, dinosaurs, birds, and mammals followed. The tree of life has many branches. Countless species have come and gone over Earth's long history. Evolution, driven by natural selection, has sculpted life into the amazing diversity we see today. Humans, Homo sapiens, are a very recent arrival on this ancient stage. Our species appeared only a few 100,000 years ago. We are part of this immense cosmic and planetary story, a story that stretches back billions of years, to the birth of the sun and the formation of the planets from a swirling disk of dust and gas, to the violent creation of our moon, to the arrival of water and the spark of life in the early oceans. It is a story of chance events, physical laws, and incredible transformations. Understanding this deep history gives us perspective. It shows us how precious and unique our planet is. It highlights the long chain of events that had to occur for us to even exist. Our planet Earth is our only home in the vastness of space. It provides everything we need to survive and thrive: air to breathe, water to drink, food to eat. As we learn more about Earth's past, we also learn more about its present and its potential future. Human activities are now changing the planet in significant ways. Climate change, pollution, and habitat destruction are major challenges. By understanding the delicate balance of Earth's systems and its long history of change, we can make better choices to protect our home for future generations. The cosmic journey of Earth and of humanity continues.